In 1985, an engineer trying to build a computer compatible with IBM's new PC-AT faced a motherboard that seemed far more complicated than the processor at its center suggested. The Intel 80286 was the part customers recognized, but the machine around it depended on a dense network of supporting circuitry. Across IBM's system board were controllers, buffers, decoders, latches, timing logic, and rows of smaller devices whose combined behavior allowed the processor, memory expansion bus, and peripherals to operate as one compatible system. IBM had not hidden this architecture. Its technical reference documented the PCAT in extraordinary detail, giving outside engineers access to schematics and descriptions of how the machine behaved. The challenge came after the diagrams were understood. Another manufacturer still had to turn that information into a motherboard that could be laid out correctly, manufactured economically, debugged when something went wrong, and trusted to behave closely enough, like IBM's machine, for existing software and expansion hardware to work. Then, chips and technologies approached the problem from a different direction. Rather than expecting every AT-compatible manufacturer to recreate much of that supporting logic from dozens of individual devices, the young semiconductor company packaged a large portion of it into 5 highly integrated chips. DataQuest described the result in striking terms. The C&T PCAT chipset replaced 63 glue logic devices and reduced the 94 devices used in the AT system board design to 36 components plus memory. The significance was larger than the component count itself. A motherboard designer could now obtain important pieces of the system logic already organized inside silicon created specifically for an AT-compatible machine. The processor still had to be selected and connected. Memory, BIOS, expansion slots, storage interfaces, and the rest of the computer still required engineering. And a poorly designed board would not become compatible, simply because 5 C&T chips were soldered onto it. What had changed was the amount of complexity waiting at the beginning of the project. Some of the circuitry IBM had spread across many devices was becoming something a manufacturer could purchase as a defined semiconductor product instead of reconstructing it piece by piece. That created an unusual situation. IBM had designed the PC-AT and established the behavior the market wanted to reproduce. Yet another company was beginning to sell part of the knowledge required to build that behavior into competing machines. An engineer looking at the 5 chipset was therefore seeing more than a cleaner motherboard. The difficult logic surrounding IBM's 80286 was beginning to become reusable. For clone manufacturers, that could shorten the distance between understanding the AT and producing one of their own. Why that mattered so much becomes clearer only when the IBM motherboard is opened up again, and the jobs hidden inside all of that surrounding circuitry are examined one by one. The IBM PC-AT looked from the outside like a faster version of the personal computer IBM had already made successful, but the move to the Intel 80286 changed much more than processor speed. The new CPU could address far more memory, work with a 16-bit data path, and enter the protected mode Intel had designed for more sophisticated software. IBM also wanted the machine to remain useful to customers who already owned PC software and expansion hardware. Making those goals coexist required far more than placing an 80286 beside some RAM. The motherboard had to become the layer that organized everything around the processor. Memory alone created a surprising amount of work. Dynamic RAM could not simply sit idle until the CPU needed it. Its contents had to be refreshed continuously. Addresses had to reach the correct memory banks at the right moment, and parity circuitry watched transfers for errors. The expansion bus added another complication. IBM widened the AT bus to support 16-bit transfers, but older 8-bit PC adapters still had to remain useful. The system therefore needed logic capable of recognizing what kind of device was responding and arranging the transfer accordingly, rather than assuming every expansion card behaved like the new hardware. Other parts of the computer needed access to the processor and memory without colliding with one another. 2 cascaded interrupt controllers gave devices many more routes for requesting CPU attention than the original PC had provided, while a pair of DMA controllers allowed certain transfers to occur without forcing the 80286 to move every byte personally. None of those controllers could simply act whenever they wanted. Bus ownership, addresses, timing, and control signals had to arrive in the correct sequence, or the entire machine could behave unpredictably. Even functions that seemed small added another layer to the board. The system timer supplied recurring timing events. A battery-backed real-time clock preserved the date, time, and configuration information after the computer was switched off. The keyboard controller handled communication with the keyboard while also participating in system control behavior that became important to the AT architecture. Between those recognizable devices sat the less glamorous circuitry that made them cooperate. Buffers directing signals onto and off buses, decoders deciding which device should respond to an address, latches holding information at the correct moment, and smaller logic devices producing the control signals that connected one section of the motherboard to another. IBM's technical documentation makes the scale of that coordination visible. The 80286 occupies only one place inside a much larger system containing memory control logic, DMA, interrupt handling, timing, keyboard control, CMOS storage, and the circuitry required to connect those functions to the expanded I/O channel. None of this complexity meant IBM had designed the AT badly. Much of it existed because the company was trying to increase performance and capability without casually breaking the enormous investment already forming around the PC architecture. The faster processor had to work inside a machine that still recognized earlier assumptions while supporting a much more capable system around them. That made the AT commercially powerful, but it also made reproducing the motherboard a serious engineering project. An independent manufacturer could read IBM's documentation and understand what the system was supposed to do. Yet it still had to turn those diagrams into hundreds of electrical relationships that behaved correctly together on a real board. When Dado Banatao began studying that design closely, the crowded motherboard suggested something more valuable than another opportunity to copy IBM's layout. A large amount of the complexity surrounding the processor performed recurring system functions that might not need to remain scattered across dozens of separate devices at all. Dado Banatao began studying IBM's personal computers with the instincts of a semiconductor engineer rather than those of someone interested only in reproducing a motherboard. By 1984, he had become convinced that the IBM-compatible architecture was going to support a much larger market, and he spent enough time working through the design that the project followed him home. In his later oral history for the Computer History Museum, Banatao remembered covering the family dining table with notes as he worked through what an IBM-compatible chipset would require. The PCAT caught his attention because the motherboard was so busy. The processor itself occupied only one part of a design crowded with the supporting circuitry needed to make the entire system behave correctly. To someone accustomed to thinking in integrated circuits, that complexity invited a different question. Much of the board performed recurring control functions. If those functions could be reorganized inside a smaller number of chips, the value might extend beyond one computer. Banatao began pursuing that work while involved with Mostron, a startup formed around the business of building PC motherboards. The company managed to turn the engineering into real hardware. Banatao later recalled that after roughly a year, the boards were finished and being offered at Comdex. What Mostron never acquired was enough financial strength to turn that accomplishment into a durable business. Funding remained thin, and eventually the company ran out of cash. For Banatao, the experience could easily have ended as an unsuccessful attempt to become another supplier in the rapidly expanding compatible PC market. Instead, something in the response to the product pointed elsewhere. In a later interview, he remembered being disappointed that the motherboard itself had not succeeded, but he also recalled that customers kept showing interest in the chips he had designed for it. That reaction changed what the unfinished work represented. The valuable part of Mostron did not necessarily have to remain attached to a complete board. Other companies already wanted to build PCs under their own names, choose their own layouts, and decide how their systems would be configured. What they could use was a way to avoid solving all of IBM's supporting system logic independently before reaching those decisions. Banatao still had the chipset work after Mostron ran out of money, and he remained convinced that the PCAT was the architecture worth building around. The opportunity to continue came through Gordon Campbell, whom Banatao knew from SEEK. Campbell had left that company and, according to Banatao's recollection, had become connected with a real estate investor willing to put about $1 million behind a new venture. When Campbell asked what product could be built with that money, Banatao described the chipset. The proposal was direct enough that there was little need to invent another business around it. The engineering Mostron had begun could become the product itself. That conversation helped lead to Chips and Technologies, established in 1985, with Campbell as president and chief executive, and Banatao leading engineering. Contemporary DataQuest records confirm that structure and describe the new company as developing VLSI products for IBM-compatible microcomputer systems. The important change was not simply that Banatao had moved from one startup to another. Mostron had tried to sell a motherboard built from his engineering. Chips and Technologies would instead package that engineering so motherboard makers could use it inside designs of their own. The crowded IBM PC AT board that had filled his dining table with notes was about to be reduced to a handful of merchant chips, and the first version would contain 5. When Chips and Technologies began operating in 1985, the work Banatao had carried out around the PCAT no longer had to remain attached to one motherboard. Gordon Campbell led the new company while Banatao headed engineering, and the first system logic project took direct aim at the complexity he had already spent so much time studying. Instead of recreating IBM's web of small logic devices on another board, the C&T team began moving much of that behavior inside larger integrated circuits. The result was the CS8220, a 5-chip set designed around PC or AT compatible system logic. Its significance was easiest to understand by looking at what no longer had to remain scattered across the motherboard. IBM's design used numerous devices to generate control signals, coordinate the processor with the bus, decode memory and I/O addresses, manage refresh-related behavior, buffer addresses and data, and maintain parity as information moved through the system. C&T reorganized large portions of those functions into 5 devices built to operate together. 2 of them carried most of the control intelligence. The 82C201 served as the system controller, while the 82C202 handled memory decode and I/O control. C&T's own documentation shows that together, these devices absorbed functions associated with several of the controllers used around the 80286 and eliminated much of the smaller MSI and SSI logic that IBM had required around them. The remaining 3 chips dealt more directly with signals moving across the motherboard. The 82A203 handled high-address buffering and port B functions. The 82A204 combined low-address buffering with refresh control, and the 82A205 managed the data bus and parity. Their names sound specialized because they were. Each took a collection of jobs that had previously been distributed through smaller pieces of circuitry and placed them inside a component designed specifically for the AT environment. Put together, the reduction was substantial. Contemporary DataQuest material reported that the C&T PC AT chipset replaced 63 glue logic devices and reduced the 94-device system board implementation to 36 components plus memory. The motherboard still contained far more than those 5 chips. It needed the 80286, memory, firmware, peripheral controllers, expansion hardware, clocking, and all of the electrical design required to make those pieces cooperate reliably. What had changed was where a large portion of the supporting logic now lived. Circuit relationships that IBM had implemented through dozens of separate packages could arrive already organized inside the C&T chipset. The complexity had not disappeared. Semiconductor engineers had absorbed it into silicon before the motherboard designer ever began routing the finished board. That was why the CS8220 represented something more important than a reduction in chip count. Banatao and the C&T engineering team had taken knowledge of how an AT-compatible system needed to behave and turned part of that knowledge into reusable hardware. The 5 chips did not define every detail of the computer surrounding them, and manufacturers were still responsible for producing a complete compatible system. But they no longer had to begin the project with exactly the same collection of discrete system logic IBM had used. A substantial piece of the AT architecture could now arrive from a semiconductor supplier already packaged for reuse. The real consequence of that change would become visible when motherboard companies began designing around the chipset. What had once demanded a large amount of low-level logic engineering could now become the starting point for the rest of their system. The real value of the CS8220 appeared when a motherboard engineer sat down to begin a new AT-compatible design. IBM's technical documentation could explain how the original machine worked, but without an integrated system logic solution, understanding the design was only the beginning. The engineers still had to select dozens of supporting devices, decide where they belonged, connect them correctly, and make sure the timing between them remained close enough to IBM's behavior for the finished system to be compatible. With the C&T chipset, a substantial portion of that work arrived in a different form. Instead of recreating many small control relationships from individual logic packages, the designer could begin with several large functions already organized into a set intended to operate together. That changed the shape of the motherboard project before it changed anything visible to the customer. Fewer separate packages left more freedom in the physical layout. Signals that once had to travel between many pieces of glue logic could remain inside the chipset or pass through a smaller number of external connections. The board still required careful routing, but the designer was no longer reproducing every detail of IBM's original implementation just to reach the point where the rest of the computer could be developed. Manufacturing felt the difference as well. A long bill of materials built from many small logic devices meant more parts had to be purchased, stocked, placed, and verified during production. Integration concentrated some of those functions into a much shorter list of components. The savings were not simply a matter of counting chips and multiplying their prices. Board area, assembly effort, inventory, and the engineering time spent maintaining a design could all be affected by how many separate devices the motherboard required. Debugging changed in a less obvious way. On a board assembled from many independent pieces of logic, a fault might emerge from the relationship between several devices rather than from one obviously defective part. A control signal arriving at the wrong moment, an address being decoded incorrectly, or a bus transition occurring outside the intended timing could send an engineering team through a large part of the schematic. C&T could not remove those problems from motherboard design, but by integrating many of the relationships into silicon that had already been designed as one system, It reduced how much of that low-level behavior each customer had to recreate for itself. The manufacturer was still responsible for producing a reliable computer. It needed firmware, memory, expansion interfaces, storage support, power distribution, manufacturing discipline, and extensive compatibility testing. What the chipset changed was where that work began. A company could spend less of its engineering effort rebuilding the same foundation IBM had already established, and more of it deciding what its own machine should become. That distinction gave the five-chip set commercial power. Mostron had tried to turn Banatao's engineering into one motherboard that would compete with other motherboards. Chips and technologies could sell the reusable part of that engineering to many of those competitors at once. Every customer could surround the chipset with a different board and sell a different computer, while the underlying AT system logic came from the same semiconductor supplier. The breakthrough, therefore, did not make clone design effortless. It made an important layer of clone design repeatable. Once that happened, the next question was no longer simply how much of IBM's motherboard could be purchased from C&T. It was how many other essential pieces of an IBM-compatible computer were also becoming available from companies outside IBM. By the middle of the 1980s, the importance of the C&T chipset could no longer be understood by looking only at the motherboard. Something larger was happening around the IBM-compatible PC. More of the technology required to build one was becoming available from companies that did not manufacture IBM computers at all. Intel already supplied the 80286 at the center of the PCAT. Microsoft's DOS licensing model allowed other computer makers to ship machines capable of participating in the same expanding software environment. And the success of IBM-compatible systems reinforced the value of that shared platform. The Computer History Museum describes the clone market as one in which many manufacturers licensed MS-DOS while competing through hardware of their own. Firmware had been more difficult because copying IBM's BIOS code was not a legitimate route to compatibility. Companies with sufficient engineering resources had already demonstrated another solution. Columbia Data Products created an equivalent BIOS through a cleanroom process for its 1982 compatible, and Compaq later developed its own legally reverse-engineered BIOS for the Compaq Portable. Those successes proved that IBM-compatible behavior could be recreated without owning IBM's code. But they still required each manufacturer to possess the expertise and resources to solve the problem for itself. Phoenix Technologies changed that equation in 1984. Rather than building a computer around its BIOS, Phoenix offered the firmware as a commercial product that other manufacturers could license. In Phoenix's own later account, its May 1984 ROM BIOS became the missing link that allowed OEMs to build highly compatible systems without independently repeating the same firmware development effort. The arrival of C&T System Logic fit naturally into this changing environment. A new computer company could increasingly obtain critical pieces of the compatible architecture from specialists. The processor from one supplier, operating system software from another, firmware from another, and much of the motherboard control logic from chips and technologies. Expansion cards and peripherals already designed around the PC standard filled out still more of the system. None of these pieces created a finished computer by themselves, and integrating them into a reliable product still demanded serious engineering. What had changed was how much expertise a manufacturer needed to develop entirely inside its own organization before it could begin. Evidence that the C&T approach was moving beyond theory appeared quickly. An October 1986 issue of Electronics reported that the original CS8220 had already been used in PCs from Tandy, Nippon Electric, PCs Limited, and Apricot Computer. Those companies were not producing the same machine simply because some of their system logic came from the same supplier. The chipset gave them a common foundation while leaving decisions about memory, storage, graphics, packaging, pricing, and other parts of the finished computer in their own hands. That distinction was beginning to reshape what an IBM-compatible PC actually was. Compatibility no longer had to mean reproducing IBM's physical motherboard device by device. It increasingly meant preserving the behavior that mattered to software and peripherals, while allowing different companies to implement the machine in their own way. IBM still supplied the reference against which compatibility was judged, but the engineering required to reach that reference was becoming distributed across an independent network of semiconductor, software, firmware, peripheral, and system manufacturers. The CS8220 had not created that network. Its importance came from removing one more difficult layer from the list of things every clone maker had once needed to solve for itself. As those layers became purchasable, a compatible PC began to look less like an imitation of a single IBM product, and more like a platform an industry could assemble, modify, and sell. Chips and Technologies was already preparing to push that idea further by taking functions that still remained outside its original 5-chip set and pulling them into silicon as well. The first 5-chip set had shown chips and technologies that much of IBM's motherboard logic could be treated as a reusable semiconductor product. Once that idea was working in real computers, there was little reason to stop at the functions already inside the CS82220. Several major AT support devices still remained outside the original set, occupying board space and forcing each manufacturer to reproduce another familiar section of IBM's design. C&T's next integration step was the 82C206 Integrated Peripherals Controller. Inside one device, the company brought together functions equivalent to the two DMA controllers and two interrupt controllers used in an AT, along with the system timer, the real-time clock, and CMOS storage, a memory mapper, and related control circuitry. To a user sitting in front of the finished PC, none of this was visible. To the engineer designing the motherboard, another collection of separate controllers had effectively collapsed into a single package. C&T then built that device into a more ambitious generation of system logic called the CS8221, or NEAT, the new enhanced AT chipset. The name mattered because this was no longer simply an exercise in reproducing IBM's original board with fewer devices. NEAT consisted of four coordinated components: the 82C211 CPU bus controller, the 82C22 memory controller, the 82C215 data and address buffer, and the 82C206 handling the integrated peripheral functions. Together, they allowed an AT-compatible motherboard to become more configurable than IBM's first implementation had been. One of the clearest examples involved speed. The original IBM PC AT had been designed around a processor and expansion system operating within a closely defined timing environment. As faster 286 processors became practical, simply accelerating everything on the motherboard could create problems for expansion cards that still expected traditional AT bus timing. NEAT allowed the CPU and AT bus to operate from separate clocks. A manufacturer could therefore raise processor performance while keeping the expansion side of the machine within conditions existing hardware was more likely to tolerate. The chipset also allowed command delays and memory wait states to be configured in software, giving designers another way to accommodate combinations of processor, DRAM, and peripheral hardware instead of locking every system into one fixed implementation. C&T extended that flexibility into memory. The NEAT architecture supported page and interleaved operation, could shadow BIOS code into faster RAM, and incorporated expanded memory support useful to software working within the limitations of DOS. Its contemporary databook described systems at 12, 16, and 20 MHz, while DataQuest's 1988 profile listed the commercial CS8221 at 12 and 16 MHz. The individual features were less important than the direction they revealed. The original CS82220 had mainly demonstrated how much of IBM's scattered glue logic could be condensed. NEAT was beginning to make the chipset an active framework for designing different kinds of AT-compatible computers. A motherboard maker could preserve the behaviors required for compatibility while making choices about processor speed, memory organization, and system timing that IBM's first AT had never needed to provide. The physical arrangement of IBM's motherboard mattered less as those choices moved behind a programmable layer of integrated system logic. Compatibility was increasingly becoming a result rather than a requirement to duplicate IBM's exact implementation. That distinction gave the clone industry room to become more aggressive. Once manufacturers could start from compatible system logic and then configure the machine around faster processors and different board designs, there was little reason for them to remain permanently behind the computer they had originally set out to imitate. Once compatibility could be preserved without reproducing IBM's motherboard device for device, clone manufacturers gained something more valuable than permission to imitate. They gained room to change the machine underneath the standard. IBM's PC AT had established what a 286-class compatible computer was expected to run, but it did not permanently determine how every future motherboard had to be laid out or how fast the processor had to operate. Integrated system logic made it easier to separate those two ideas. A manufacturer could work toward the electrical and software behavior required for compatibility while making different choices about memory, timing, packaging, and the rest of the finished system. By 1986, that freedom was already visible in the way compatible machines were being sold. PCs Limited offered an 8 MHz 286 system running at the same processor speed as IBM's contemporary AT for a base price of $1,495. A complete configuration with a monochrome display and 30 megabyte hard disk was advertised at $2,195, while the Los Angeles Times listed IBM's suggested price for a 30 megabyte AT with less memory and no display at $5,295, noting that IBM systems could be discounted. More revealing than the price difference was what sat beside the 8 MHz model in the same product line. PCs Limited was already selling 10 and 12 MHz AT compatibles and preparing a 16 MHz version. The company was no longer asking only how cheaply it could reproduce IBM's machine. It was asking how far the compatible architecture could be pushed, while still delivering the software environment customers expected. Larger manufacturers were moving in the same direction. Compaq's 286 family included an 8 MHz Desk Pro as well as a 12 MHz version, and its technical documentation explicitly described the faster machine operating at either 12 or 8 MHz. The significance was not simply that another company had found a higher clock rate. Once a compatible manufacturer could choose faster processors, different memory arrangements, and its own board implementation without abandoning the AT ecosystem, IBM's original design stopped functioning as a ceiling. The word clone increasingly concealed how much engineering freedom these machines could contain. Buyers might still choose them because they ran familiar DOS software and accepted familiar expansion hardware. Yet the hardware beneath that compatibility could now evolve along a path IBM had not chosen. Chipset technologies was only one part of that development, and not every faster AT-compatible system depended on C&T silicon. Its contribution was to make one difficult portion of motherboard engineering available as merchant system logic, reducing the amount of IBM's implementation that another manufacturer had to recreate before it could begin making different decisions of its own. By the late 1980s, that distinction was becoming increasingly important. Compatibility had begun as the requirement that allowed clone makers to enter IBM's market. Once they were inside, it became the foundation from which they could compete on more than imitation. A manufacturer could preserve the standard customers wanted while changing the computer underneath it. At that point, the most dangerous compatible machine for IBM was no longer the one that copied the AT most faithfully. It was the one that could remain compatible while moving beyond it. By 1987, the danger facing IBM was no longer simply that other companies could manufacture cheaper versions of its computers. Something more fundamental had happened to the architecture itself. IBM still provided the reference against which compatibility was judged, but increasingly it did not control the engineering path manufacturers used to reach that result. The distinction mattered because every compatible machine strengthened the same platform, whether IBM had built the computer or not. Software developers had more reason to support the environment as the installed base expanded. Peripheral companies could design hardware for a market much larger than IBM's own shipments. System manufacturers could enter that market without reproducing every layer of IBM engineering internally. The compatible PC was beginning to generate momentum outside the company whose initials were still used to describe it. IBM's own history acknowledges how quickly this happened. After the extraordinary success of the original PC, clones began taking market share, and by 1986, IBM says its dominance of the sector had already withered. The response became visible the following year with the Personal System 2 family. PS2 introduced several technologies that would prove important well beyond IBM's own machines, but its higher-end models also carried a new expansion bus called micro-channel architecture. MCA offered technical improvements over the aging AT bus, including a wider 32-bit path in appropriate systems and more sophisticated configuration. Yet IBM was not thinking only about performance. Its own account states that one goal of the new architecture was to make cloning more difficult. That goal revealed how much the competitive problem had changed. IBM could design a new bus, but it could no longer assume that the rest of the PC industry would simply follow it. Clone manufacturers had accumulated their own engineering organizations, customers, suppliers, and economic interests around compatibility with the existing AT world. Moving to a proprietary architecture meant asking that entire network to abandon some of the backward compatibility that had helped it grow. The industry answered by developing alternatives. In 1988, 9 major compatible manufacturers jointly announced ISA, a 32-bit expansion architecture intended to provide a path beyond the AT bus while preserving compatibility with existing ISA hardware. IBM's history records the announcement as a direct rival to Microchannel, while contemporary industry analysis identified Compaq as the leader of the consortium. Chips and Technologies was only one contributor to the larger transformation that made such independence possible. Its 5-chip set had not caused IBM to lose control of the PC market, and the clone ecosystem depended on many technologies, companies, and earlier compatibility breakthroughs. What C&T had demonstrated was narrower but important. Even the complicated system logic surrounding IBM's processor did not have to remain tied to IBM's motherboard implementation. It could be turned into merchant silicon, sold to competing manufacturers, and then developed further without waiting for IBM to redesign the original machine. Once that idea spread, motherboard logic became another layer of the PC that independent suppliers could improve. The consequences were now visible far beyond the 5 chips with which the story had begun. IBM compatibility still mattered enormously, but the industry capable of producing it had become larger than IBM's ability to direct it. What remained to be understood was why that small act of integration, moving dozens of motherboard functions into reusable silicon, would outlast the particular chipset that first made it practical. The 5-chip set that looked so remarkable in 1985 did not remain the final form of PC system logic for very long. Chips and Technologies itself kept integrating more functions, first through products such as the 82C206 and NEAT, and later through system logic families built for newer generations of Intel processors. By 1990, DataQuest credited the company's original AT chipset with reducing development time, board space, and manufacturing cost, while helping manufacturers build compatible 286 systems that could run considerably faster than IBM's first PC AT. The 5-chip count, therefore, was never the lasting achievement. Semiconductor integration would continue making yesterday's collection of components look unnecessarily complicated. What endured was the idea behind the original design. When Banatao studied the PC-AT, he saw a motherboard whose complexity had been distributed across many separate devices. Chips and Technologies treated a large portion of that complexity as a recurring engineering problem that did not need to be solved independently by every company hoping to build an IBM-compatible machine. Its engineers could solve much of it once, place the resulting behavior inside silicon, and sell that silicon to manufacturers designing computers of their own. That only worked if integration preserved the compatibility customers actually cared about. Banatao later recalled that software of the period could depend directly on hardware behavior at the register level. So simplifying the implementation required knowing which behaviors could safely change and which ones software expected to remain intact. His account of the C&T work makes clear that integration was therefore not merely an exercise in removing chips. It required understanding where the boundaries of compatibility really were. That distinction explains why the breakthrough mattered beyond one successful semiconductor product. IBM had published the architecture and established the machine the market wanted to reproduce. The chipset allowed another company to take some of the difficult engineering required to reach that behavior and turn it into merchant silicon. A motherboard manufacturer still needed a processor, memory, firmware, storage support, expansion hardware, electrical design, manufacturing, and extensive testing. Nothing about building a reliable PC became trivial. What changed was the starting point. A company no longer had to reconstruct the same large layer of motherboard control logic before it could begin making choices of its own. Part of that foundation could be purchased. Once the same principle spread across the compatible PC industry, the physical implementation beneath IBM-compatibility became increasingly free to evolve. Chipsets absorbed more functions, system designers gained more flexibility, and later generations would integrate responsibilities that once required entire groups of motherboard components. The particular chips changed repeatedly. The abstraction survived. That is where Banatao's contribution fits most clearly into the history of the PC. He did not invent the clone industry, and Chips and Technologies did not single-handedly take control of personal computing away from IBM. IBM's published architecture, Intel processors, Microsoft software, independent BIOS development, peripheral standards, motherboard manufacturers, semiconductor suppliers, and intense market competition all contributed to that transformation. The C&T breakthrough solved one specific but important part of the problem. It showed that complicated motherboard behavior could itself become a reusable product, available to many competing system builders. In doing so, it reduced the amount of low-level system engineering that had to be recreated before another manufacturer could begin designing its own compatible machine. What had started as a crowded collection of logic surrounding IBM's 802.86 became something a semiconductor company could package, and an entire industry could build around. IBM had defined the AT motherboard. Banatao helped turn its complexity into a product the rest of the PC industry could build upon.